Hmm. Okay, so in our last class we were discussing about the conformational analysis of perhydrophenanthrene. So here, if there is a two dots like this, it indicates that cis. Similarly, if there is no dots, also indicates cis. If there is a one dot, it indicates that trans. And here there is no dot, but here there is a dot, but then it should be a transoid.
Sir, your voice is not.
Uh,
Your voice is not clear, so.
1 minute. Okay, now you tell me, is it okay? I'm audible. Hello.
Yes, sir, it is audible.
Now it is okay. I'm audible. Am I audible?
Yes, sir.
Okay, fine. So conformational analysis of perhydrophenanthrene. So here, if there is a two dots like this, it's a cis one. If there is no dots, then also it's a cis. If there is a one dot like this, then it is a trans. Okay, that's what you need to remember. And when you are comparing here, so here dot is there, but here there is no dot, then it's called a transoid. If there is a dot here, then here also a dot, then it should be a cisoid. So this will be the nomenclature of this fused molecule. Similarly, this will be the trans, cisoid, trans. Okay, because two dots are there. Similarly, here you can say this is the trans, this also a trans, and both the thing is it should be. See what is that? This is a there is no dot, but here there is a dot. It should be transoid. So trans, transoid, trans will be the nomenclature of this mighty. So similarly, in this is trans. This one will be the cis, and when you are comparing these two, it is a cisoid. So then this is a cis, this one is trans. When you are comparing these two, this is a cisoid, cisoid trans. Similarly here, this is cis, and this one also cis. And when you are comparing these two, it's a transoid. So this is how you can nomenclate, give the names for the what you call fused molecules. So with this, I will go to the another concept called prochiral. Okay, 1 minute. Okay, now. So prochiral, okay, prochirality. So prochirality means the conversion of in a single step. If we are able to convert a non-chiral compound to chiral compound, then such process is called prochirality. And this type of compounds is called prochiral compounds. Any molecule or compound which can be converted into a chiral molecule in a single step, such process are called prochirality. That phenomena is called prochirality. Normally, many a times a carbonyl compound will be the prochiral compound. Okay, so here what you need to remember, any compound or molecule which can be converted into a chiral molecule in a single step is called prochirality. Okay, and the phenomena is called prochiral phenomena. Okay, so many a time a carbonyl compound will be the prochiral compound, and this will be the chiral compound. And okay, I will go to the next slide. So here you can observe that there are four hydrogens are there. This molecule is not a prochiral one. Similarly, you can observe that here ethene molecule, this also not a prochiral molecule. Of course, this also not a prochiral molecule. But here you can observe that two different substance, two different groups are there. And here I marked as a HA and HB. Suppose if you are replacing HA with bromide, then the obtained compound is S configuration. So that is the reason we can say that HA is the pro S. Similarly, if we are replacing HB with bromide, the obtained compound is R configuration. So we can say that it's a pro R. So then this type of molecules also a prochiral molecule, because in single step we are able to convert this molecule into a chiral molecule. So I will go to the next slide. So here, I think you know that enantiomers. Enantiomers are means non-superimposable mirror images to each other are called enantiomers. So in this one as well as this one, both are enantiomers because this is having a S configuration. This one will have a R configuration. What is the difference? You can just observe that here a methyl group is away from the observer, but whereas here the methyl group is towards the observer. Okay, so that's the only difference. Because of that only the configure what you call configuration changes, isn't it? So this here is a S and here is the R1. How you can find that this is the S configuration? If you want to find that S configuration, you have to convert into a this form. I think you can here CF3 is there. This also is CF3, and this is Cl, the left side Cl, H, and this is the away from the observer. So this you need to write in a convenient way to assign the configuration. So how you should be this is constant, but these groups are rotated in a clockwise direction. That means Cl is going over here, H is coming over here, CH3 is comes to this position. Why we need to do that? Always keep the least priority should be this position. Then your assigning R and S on a paper is good. Okay, so now you can give the priority. This is the first priority, this is the second priority, and this will be the third priority. So it will go in a anti-clockwise direction. That is the reason this is S configuration. If you this is the S means this is also a S configuration. Similarly, you can also find the S configuration R and S to this moiety. How you can find out? So this as well as this. What is this actually? Okay, I rotated one. Well, what is that? Oh, it's not rotated, isn't it? Okay. So that means Cl should go over here, H should come over here, CH3 should come over here. So that means CH3 should here, Cl should here, and then H should be here. So what is that? Cl is 1, and so that means you are getting a S configuration itself. So that means this is not the one. You have to take this as the molecule here. Then when you are taking this molecule as here, what will happen? So you cannot assign the configuration here. There should be a movement. How it will move? Okay, now it's okay, fine. So you have to assign the configuration. One, this will be the 1 position, this will be the 2 position, this will be the 3 position. So that means it's moving in a clockwise direction, right? So what you need to account here, so you have to account so don't take this, okay? You have to take this, okay? So this this one will have a R configuration. Okay, right. So that what it means, I will take a pointer. Right. So this as well as this is a enantiomers, and this will have a R configuration. This will have a S configuration, and these two are enantiomers. So what are enantiomers? Give example means you can give these two, and assigning R and S, you have to convert. You have to convert into a this part. So always keep here a least priority group. Okay. And you have to keep this as a standard, and the remaining three you have to rotate it in such a way that least priority should attain this position. Then you can give the priority numbers and check the clockwise or anti-clockwise one. So with this, I will go to the next slide. So here you can observe that I'm using the one terminology called enantiotropic phases and enantiotropic phases. So that means you can consider that two groups are there here, Cl and Cl. If you are replacing one Cl, you will end up with one enantiomer. If you are replacing other Cl, you will end up with another enantiomer. That is the reason this molecule is enantiotropic molecule, and this phenomena is called enantiotropic uh, phenomena. So, but here homotropic and heterotropic. Why it is homotropic? Because two groups are same. That is the reason it's homotropic. So this process is called enantiotropic one. Why? Because you are getting enantiomers as the compound. So here one should replace Cl with H. How you can replace? Maybe by doing reduction, it is possible to replace Cl with H. More particularly, hydrogenation in presence of palladium charcoal or platinum charcoal, it is possible. Suppose this chloride is replaced, then it is called R configuration you are getting. That means this is the compound is obtained. So if you want to know the configuration of this, you have to convert into a what you call fly-edged structure. So this Cl should be the towards the observer, and these two groups are horizontal towards the observer. These two groups are away from the observer. So then this you have to keep it as such. You have to move this compound. So that means this Cl is coming over here. H will come over here. C2Hy. So that's what this. So then you can assign. This is the first priority. This one will be the second priority, and this one will be the third priority. Then the movement is in a clockwise direction. That is the reason this is called R. So then, so if you are replacing this Cl, you will end up with R. If you are replacing this Cl with hydrogen, you will end up with S configuration. So this is the one. So that is the reason these two products, this one as well as this one, is the enantiomers. Okay, because this is the S configuration, this is a R configuration. And how you can find that this is S? So this is nothing but a this moiety. Then afterwards, what you need to do? You need to rotate this in a clockwise direction until getting H is here. So here you can find that H is down. Now you can assign the numbers sequence rule. This is 1, this is 2, this is 3. So that means there is a movement in a clockwise anti-clockwise direction. So this is S configuration. So if there is a question like enantiotropic phases, explain enantiotropic phases with an example means you have to write this. Okay. So then I will go to the next step. So next step is about the, I think you are aware about the diastereomers. Diastereomers mean non-superimposable, not a mirror images to each other are called diastereomers. And here, what you need to remember, diastereotropic phases. Suppose a prochiral moiety, if it is attached to a chiral compound, then such compounds are called diastereotropic phases. And if you are replacing here for any of the hydrogen with a different group, you will end up with diastereomers. Okay, so this is about the diastereotropic explanation with an example. But you can say that if there is a prochiral moiety, if this is attached to a chiral compound, then this type of molecule is called a diastereotropic molecule. And if we are replacing any of the hydrogen, you will end up with the diastereomers. Okay. So here, suppose if we are replacing this H is deuterium, it is possible. Why? Because when you are treating this moiety with D2O, D2O means it's called heavy water. It is possible to replace with hydrogen with deuterium. So suppose this hydrogen is replaced with deuterium. This is the compound you are getting. If you want to know that whether this chiral center is R or S, then you have to convert this moiety into this param. Then after converting this param, you have to check. So here there should be a least priority group. In this least priority group means H should come over here. Then what you need to do, you have to keep this as a standard and you have to move these groups in a clockwise direction. So H will come over here, D will come over here, CHBr will come over here in this one. Then again one more rotation, CHBr will go over here, H will come over here, D will come over here. So now at this moment, you give the priority. This is the one, this one is 2, this one is 3. So what is happening? It's a clockwise direction. So that is the reason it's called R configuration. This is R. So you can also, here also a chiral compound is there. Okay, that is the reason these products are diastereomers. So similarly, if this hydrogen is replaced with the deuteronium, then this is the product is obtained. If you want to know that a newly formed chiral is R and S, then you have to convert into this param. So this will be further converted into this param to assign the priority. Here, this will be the 1, this will be the 2, this will be the 3. That means it's in a anti-clockwise direction. So that is the reason this is called S configuration. So overall, if there is a question like explain diastereotropic phases with an example, means you have to take a molecule like this and you have to treat with D2O, you will end up with the diastereomer. You have to mention the R and S. Okay, so then you have to do this process. Okay, this process is need not to be necessary in writing the answer, but this practice is required for you to know whether the chiral compound is R or S. Okay, so then with this, I will go to the next slide. So here, one more terminology I will use it. So what is that? Homotropic and heterotropic. So how do you found that? Homotropic means you can observe that two groups are identical one. So you can easily find out, and these are identical one. And also you know that a plane of symmetry. If there is a plane of symmetry like this, you can, of course, this moiety will have a plane of symmetry. So that is the reason I have given a heading homotropic phases with symmetry. So there is a symmetry, plane of symmetry. Okay. Here also you can observe that there is a plane of symmetry. Here also you can observe that there is a plane of symmetry. Okay. And what we can say that these are the examples, homotropic phases with symmetry. Symmetry is there. But here I will mention one more terminology, heterotropic phases without symmetry. So you can observe that this is a different group, this is also a different group. And one more thing, this homotropic phases contains only one phases, whereas heterotropic phases contain two phases. One is called re phase, another one is called C phase. How do you find the re phase and C phase? If you just look into the substituents present to the carbonyl compound. So you know that this is a carbonyl compound. There is a deuteronium and there is a hydrogen. So if we are looking into the mass, this is 1 and this is 2. That is the reason this takes a priority. That is the reason there will be a movement in a clockwise direction. So that is the reason this space is called rephase. And similarly, if deuteronium is on the left hand side, so that's what I'm written here. If deuteronium is on the left hand side, then the movement order is this way. That means it's an anti-clockwise direction. So that means then it's called a C phase. So what it means? It means that heterotropic compound contains two phases. One is rephase, another one is C phase. Whereas homotropic phases contain only one phase. And these homotropic phases contain plane of symmetry. Heterotropic phases does not have a plane of symmetry, but this contains two phases. So I am taking few more example. So you can also observe that CH3H acetaldehyde. So in this, you can observe that there will be a movement from oxygen to CH3, CH3 to hydrogen. So that means it's a clockwise direction. Then we can say that rephase. So you can observe that there will be a movement like this. It is in a anti-clockwise direction. That is the reason it's C phase. So here I am taking the benzaldehyde. There will be a movement in a anti-clockwise direction. Sorry, clockwise direction. It's called rephase. And here also you can observe that there is a anti-clockwise direction. It's called as a C phase. So this is the difference. There will be a question on 2 marks or one marks question. Then you should be able to explain it. So what is heterotropic phases? Give an example. And how many phases are present in heterotropic? So then you have to take examples this. You have to mention that in heterotropic phases, two phases are there, V phase and C phase. That's what you have to explain. So with this, I will go to the next slide. So next slide, I'm taking a enantiotropic phase. So you can observe that suppose, of course, you know that this is a heterotropic phase, heterotropic molecule, and this molecule contains two phase. One is rephase, another one is C phase. Suppose if there is a nucleophile may be a hydrogen, maybe a CN minus, or maybe a amino, whatever it is. So there is a possibility of attacking from the back side as well as the front side. If it is attacking from the back side means this is the position, it will come over here. So backside means it will be away from the observer. That you need to remember. If a nucleophile is attacking from the backside means it will be away from the observer. If the nucleophile is attacking from the front side means it is towards the observer. These two difference you have to remember. And you can observe that these two are the products obtained ones are the enantiomers. So that is the reason it's called enantiotropic phases. So explain enantiotropic phases with an example means you can take these two examples and you can treat with a nucleophile and you will end up with enantiomer. That's what you need to mention. And also you should be able to write a rephase of benzaldehyde and the C phase of benzaldehyde. In other way, you can also remember that if there is a attack from the hydrogen side, means less hindered side is called C phase. If there is an attack from the more hindered side is called the rephase. So that also you can remember. So here I have taken Cn minus as a nucleophile and the obtained products are enantiomer, and this process is called enantiotropic phases. And similarly, if there is a change in nucleophile, here I am taking a Grignard reaction. So CH3 minus always attack from a front side attack. It's also called a C phase attack, and the product obtained one is this. Okay. So with this, I will go to the next slide. So next slide, I'm taking a diastereotropic phases. This moiety is called the diastereotropic molecule. More particularly, this site is called diastereotropic site. So here there is a possibility of attacking Cn minus from the C phase side, from the re phase side. Okay. And one more thing, here there is a possibility of getting erythro. Erythro means if the two hydroxy group is on the same side is called erythro. If the hydroxy groups are in the opposite side is called trio. It is not restricted to the hydroxy group itself. These groups may be a bromide or methyl or ethyl. Overall, trio means the priority groups are in opposite side. So trio will be the form. And here one more thing is called, overall you need to remember that this moiety is called a diastereotropic molecule, and this site is called diastereotropic site, and nucleophile can attack from either side, this side as well as this side. Attack of this side is called C phase, attack of this side is called re phase. So that is the reason it is in diastereotropic, it is possible to get erythro as well as a trio. And I will tell you maybe in the next slide, I will take up one rule called Crams rule. So this is the Crams rule. So here, Crams rule means it is possible to predict the major product. So this can be explained by taking the Newman's projection formula. So what we can say that when a ketonic, okay, so when a ketonic group is attached to a chiral center, this is the ketonic group is attached to a chiral center. If it undergoes a nucleophilic addition with organometallic or metal hydride, two diastereomers products are erythro and trio is product, trio product formation. But out of which one is the predominant, that predominant is predicted by Crams rule. Okay, so how we can explain? So let's take the example of this. So this is a chiral compound. This chiral compound is attached to a carbonyl compound. And here I'm written a Newman projection formula. And here you can observe that this is the H, and H is a small group. Okay, so that is the reason, and nucleophile is attacking from here. So this phase is called the C phase. So nucleophile is attached from a C phase. That is the reason it will give you a intermediate like this. So this intermediate can be converted into this form. So this again further converted into this. How you want to check? So maybe you can observe that, look here, when Cn minus is attacking here, OH is going this side and Cn will come over here. That's what I have written here. So here you need to remember that front carbon and back carbon is represented in a circle. So these groups are back carbon substituents and these groups are called front carbon substituent. And here, so this one is rotated in a clockwise direction. Cn is coming over here. When Cn is coming over here, this H will come over here, OH will come over here. That's what I have written here. So from here to here, so front carbon is same, but back carbon is rotated in such a way that the phenyl should come over to here. When phenyl is coming over to here, then CH3 will come to this position, H will come to this position. That's what I have written here. So when you are converting Newman projection formula into a Fisher projection formula, say the front carbon you can write Cn, that is this, OH, right hand side, that is this, hydrogen, left hand side, that is this. Similarly, where back carbon, how you can convert phenyl group is down, you have to write CH3, left hand side, H, right hand side. This is how you can find out. And here you can observe that the priority group is on the left hand side. Here the priority group is on the right hand side. Since the priority groups are in opposite direction, so we can say that this is a trio. So what it means? It means that Crams rule can, using Crams rule, one can predict the major product, that is trio, and this is the mechanism. So this is again a Crams rule is explained with the help of the example. So maybe in the next slide, I will take one more example. So this is one more example. Only the substituent is different. Here the deuterium is there, and here ethyl is there. That's all. That is the difference. So then what will happen? Again, you can convert this into a Newman projection formula like this. So here you can observe that deuterium is a small group compared to the ethyl. Then what is called as a nucleophile is attacking this way. So once this is attacking this way means OH will come over here, CH3 will sit over here. So that's what I have written here. So from here to here, there will be a movement. What is that movement? CH3 should come over here. So that's what I have written here. So what is that? Means it's a what we can say that it's a rotation. So CH3 is here, OH is here, hydrogen is here. The back carbon is same position. There is no changes. From here to here, back carbon movement. That means this is moving. Phenyl is moving like this. If the phenyl is moving like this means deuterium will come over here. That's what I have written here. So from here to from Newman projection formula to 3O. So how CH3 is this? OH is the left hand side, H is on the right hand side. Similarly, phenyl is down. The left hand side is deuterium. Ethyl is this one. Suppose if you want to know how one can write a Sahar's projection formula into a Newman projection formula, you have to view from this side. If you are viewing from this side, you can observe that ethyl group is on the left hand side. So that is the reason ethyl group is on the left hand side. This is how you can convert a Fisher into a Newman, Newman into a Sahar's. And this is an example of Crams rule, how it is possible to get a 3O as the major product. 3O as the major product because a nucleophile is attacking from the less hindered side. So this is another example. So I will take one more here. So here I'm taking one more. So the group, methyl group is different. Phenyl is here, but here one more substituent is there. That's all. So again, here also you should view from here. When you are viewing from here, CH3 is coming on the left hand side. So this is the left hand side. And when you are viewing from here, deuterium is on the right hand side. Of course, phenyl is down. And CO is this, CH3 is this. So this is how you can write, you can convert SAR's projection formula into Newman projection formula. But here, what is important? What is that? It is a nucleophile, okay? Ethyl magnesium bromide. It is attacking from the less hindered side. So then what you are getting? Hydroxy group here. Hydroxy group is on the left hand side. Left hand side is coming, and this is the one is octane. Then afterwards, what will happen? What is called? It will be movement. How it is moving? The ethyl group will come over here. Hydroxy group come over here, and then what is called CH3 will go over here. So that means when you are writing from this to this, it will be an anti-clockwise movement. So then only this form, staggered form is octane. This is eclipse form. This is a staggered form. So from here to here, back carbon rotation, phenyl should come over here. If the phenyl is coming over here means deuterium will come over here. That's what I have written here. So from conversion of Newman projection formula to Fisher projection formula, so you can write ethyl is this, hydroxy right left hand side, that is that, CH3 is this, and then here back carbon right, ethyl group, phenyl group is on the down, deuterium is on the left hand side, and the CH3 group is on the right hand side. So here you can, here also you can observe that this is again, this is also a 3O compound. Why? Because why it is 3O? Between CH3 and deuterium, this is the bulky, and between CH3 and OH, this is the bulky. So these bulky groups are in opposite direction. That is the reason this is a trio. So this is these three examples I explained as per the Crams rule. So let's go to the another concept called Prelag's rule. Prelag's rule for asymmetric induction. So if correlate the configuration of chiral alcohols with those of alpha hydroxy acids, for example, mandelic acid and atrolactic acid. When a phenyl glyoxylic acid is esterified with an optically active alcohol, for example, menthol, we get a keto ester. Further, a Grignard addition to this, followed by hydrolysis, gives configurationally stable atrolactic acid. Therefore, Frilax rule correlate the configuration of hydroxy acid with that of the alcohol. So this is about the Prelag's rule. So here, this sentence words I am explaining in terms of structure. So this is the menthol. It is a optically active. This is the glyoxylic acid. And so what it's a simple esterification. Alcohol react with acid giving rise to ester. So this ester, when it is treated with methyl magnesium bromide, what will happen? Me, carbanion will